This is the third and last video about projectile motion. Now let's say now that we have a projectile launched at an angle. Our last video we investigated a projectile that was thrown horizontally. Now let's say it's launched at an angle. In this case, we've got a initial velocity of 15 meters per second, and the angle is 35 degrees above the horizontal. And it's launched from the ground is flat, and we want to know how far it goes before it returns to the flat ground. So there's the ground, our initial velocity is 15 meters per second. That angle is 35 degrees. It's going to take a parabolic trajectory like so, and we want to know delta x, how far it goes. Now you recall from previous videos that the x component of the velocity is constant, and so let's go ahead and find that. We've got the velocity drawn as a vector here. Here's our coordinate system, x and y. So there's vx, and there's v naught y. Looking at that little triangle there, it's pretty easy to tell that vx is 15 times the cosine of the launch angle, 35 degrees, which we can put in our calculator and find that it is 12.3 meters per second. And v naught y is 15 times sine of 35 because it's opposite the angle, and it is 8.6 meters per second. So we know that the x component of velocity is constant, so therefore we can say that vx times t equals delta x, where t is the time in the air. Now in order to get the time in the air, we have to use the y component of the velocity. So we know, first off, and this is the tricky part, that delta y is equal to 0. Because it returns to the same level as it started at. So its net up and down displacement is nothing. Ends where it started. And we know v naught y is 8.6 meters per second. And we also know that ay equals negative g. And what we're looking for is t. And for this, we'll want to use the second kinematic equation. So we'll say that 0 equals v naught y times t minus 1/2 gt squared, and solve for t. It's quadratic, so we're going to solve it by factoring. And we can factor a t out of it. So we have v naught y minus 1/2 gt equals 0. That means at least one of these factors must equal 0. So either t equals 0 or v naught y minus 1/2 gt equals 0. Now, if t equals 0, that's clearly not the answer we want, because a projectile does spend some time in the air. But what that corresponds to is the other time at which the projectile's displacement is 0, which is before it's launched. And then, but we want to pick the other one, and we'll solve that, and we'll get t equals v naught y times 2 over g. And then we'll take that, we'll plug it into this equation, and we'll get delta x equals, let's see, vx times t, vx times 2 v naught y over g. At this point, we could plug in numbers and solve and get a number. But instead of doing that, what I'm going to do is I'm going to use these expressions for vx and v naught y. So vx is the initial speed times the cosine of the launch angle, and vy is the initial speed times the sine of the launch angle. And so we get v squared over g times 2 cosine theta sine theta. And you might remember from pre-calculus last year that 2 cosine theta sine theta is equal to the sine of 2 theta. So v squared over g times the sine of 2 theta. That's not an equation to memorize, but let's think about what it means for a second. Actually, that's what I'm going to ask you in class tomorrow, so make sure you come to class with an answer for this. At what angle will the range be maximum for a given speed? Hint, it's not 0 and it's not 90. Figure that out. For this problem, if you plug in numbers, you get the horizontal displacement being 15 squared divided by 9.8 times the sine of 70 degrees. That's 2 times 35, and we get a range of 21.6 meters. So far, so good. Now let's take the same projectile. Oh, wait. Not the same projectile. Deleted a slide there. Let's say we want to get a trajectory. So you want to know how high the projectile is at a particular horizontal position. So before, what we've gotten is x as a function of t and y as a function of t, given by the equations x equals vx times t and y equals v naught y times t, not plus, but minus 1/2 gt squared. What we'd like to do now is get a function for y from x. So in other words, y as a function of x instead of x and y as functions of t. This would tell us the shape of the trajectory, although it wouldn't tell us where it is at any particular time. To do this, what we've got to do is substitute and get t out of this. So the equation in x becomes t equals x over vx. And what we'll do is we will plug that into the equation for y. So we have v naught y times x over vx minus 1/2 g times x squared over vx squared. Or writing it, cleaning it up a little bit, v naught y over vx times x minus g over 2vx squared times x squared. If you look at the form of this equation, you've got a parabola because there's an x squared term, it's quadratic. You also notice that the x squared term is negative, which means it's a downward opening parabola. And you can figure out a few other things from this if you're clever, but that's the important part, is that any projectile will travel on a parabolic path. Now, at this point, you should be able to, for tomorrow, you should be able to work all the Chapter 4 problems, but what I'm going to be checking is problem 23.